Hi, welcome back. So let's talk about several different tools that we're going to use on top of the Hadoop framework. With the evolution of computing technology, it is now possible to manage immense volumes of data that we previously could only handle by supercomputers, and it would be really, really expensive to do. So prices and systems have dropped, and the results, these new techniques for distributed computing can come along and actually kind of became a mainstream. So the real breakthrough happened when the companies like Yahoo and Google and Facebook came to realization that they needed to do something in order to monetize these massive amounts of data they were collecting. So this is where all of these applications have evolved over time, as we have seen through numerous of these organizations. So let's talk about the Apache Scoop. Scoop stands for Sequel to Hadoop. It is a straightforward command line tool that has several different capabilities. It lets us import individual tables or entire databases into our HDFS system, and it generates Java classes to allow us to interact and import data with all of the data we imported. It provides the ability to import SQL databases straight into the Hive data warehouse, which sits within the HDFS system. After setting up an import job in Scoop, which we will do at the exercise at the end of this module, you can get started to work with the SQL database-backed data within your Hadoop environment and use MapReduce to launch all kinds of fun jobs on this data. So next up is HBase. HBase is a key component of the Hadoop stack, as its design caters to applications that require really fast, random access to the significant data set. HBase, if you remember, we talked about it earlier, is based on Google's Big Table, and it can handle massive data tables combining billions and billions of rows and millions of columns. So next up, let's talk about Pig. It's a scripting language. It's really a high-level platform for creating MapReduce programs using Hadoop. This language is called Pig Latin, and it excels at describing data analysis problems as data flows. Pig is complete in that you can do all the required data manipulation within the Apache Hadoop just by using Pig. In addition, through the user-defined functions facilities in the Pig, you can actually have Pig involved code of many different languages like JRuby, JPython, and Java. And conversely, you can execute Pig scripts in other languages. So the result is really that you can use Pig as a component to build much larger, much more complex applications that can tackle some real business problems. Again, we're going to play with that in the next couple of exercises and experience kinds of things we can do with Pig. A good example of Pig application is the ETL transaction model that describes how a process will extract data from a source, transport it according to the rule set that we specify, and then load it into a data store. Pig can ingest data from files, streams, or any other sources using the UDF, or what we mentioned previously, a user-defined functions that we can write ourselves. Once it has all the data, it can perform, select, iterate, and do any other kinds of transformations over that data. Again, the UDF features can allow us passing data to more complex algorithms for more complex transformations, and it can then take all of these transformations and store it back onto the Hadoop data file system. So next, let's talk a little bit about Hive. The Apache Hive data warehouse software facilitates querying and managing large data sets residing in our distributed file storage. It actually provides a mechanism to project structure on top of all of this data and allow us to use SQL-like queries to access the data that we have stored in this data warehouse. This query language is called HiveQL. At the same time, this language also allows us traditional MapReduce programs to plug inside the custom mappers and reducers when it's inconvenient or too complex or really inefficient to express the logic we would like to express in processing our data within the Hive SQL language. Now let's talk about Oozie. Oozie is a workflow schedule system that manages all of our Apache Hadoop jobs. Oozie workflow jobs are what we call DAGs, or directed acyclic graphs. Oozie coordinated jobs are recurrent Oozie workflows jobs that are triggered by frequency or data availability. It's integrated with the rest of the Hadoop stack, supporting several different Hadoop jobs right out of the box. You can bring in Java MapReduce, you can bring streaming MapReduce, you can run Pig and Hive and Scoop and many other specific jobs on the system itself. It's very scalable and reliable and quite extensible system. Next up is the zookeeper. Well, we have this large zoo of crazy wild animals and we gotta keep them in and keep them somehow organized. Well, that's kind of what the zookeeper really does. Apache Zookeeper provides operational services for the Hadoop cluster. It provides a distributed configuration service, a synchronization service so he can synchronize all these jobs, and a naming registry for the entire distributed system. Distributed applications use the Zookeeper to store and mediate updates to important configuration information on the cluster itself. And last but not least, Flume is a distributed and reliable available service for efficiently collecting, aggregating, and moving large amounts of data. It has a simple and very flexible architecture based on streaming data flows. It's quite robust and fault tolerant, and it's really tunable to enhance the reliability mechanisms, failover, recovery, and all the other mechanisms that keep the cluster safe and reliable. It uses a simple extensible data model that allows us to apply all kinds of online analytic applications. So we have talked a little bit about the Hadoop Cloudera components, and we have just covered majority of them. There's many more. We feel like these are the basic ones that would enable us to do most of the kinds of jobs and applications that we would like to perform on this particular cluster. There is two other little pieces, little components of the Cloudera Hadoop stack that I would still like to bring up, although maybe you wouldn't necessarily consider it one of the core components. First one is Impala. Impala was designed specifically at Cloudera, and it's a query engine that runs on top of the Apache Hadoop. The project was officially announced, I think, at kind of the end of 2012, and became a publicly available open source distribution. Impala brings scalable parallel database technology to Hadoop and allows users to submit low latency queries to the data that's stored within the HDFS or the HBase without requiring a ton of data movement or manipulation. Impala is integrated with the Hadoop, and it works within the same file system, within the same formats, metadata, all the security and reliability resources and management workflows. It brings that scalable parallel database technology on top of the Hadoop. It actually allows us to submit SQL-like queries at much faster speeds with a lot less latency. So the additional components we haven't mentioned yet is Spark. Although Hadoop captures the most attention for distributed data analytics, there are now a number of alternatives that provide some kind of interesting advantages over the traditional Hadoop platform. Spark is one of them. Spark is a scalable data analytics platform that incorporates primitives for in-memory computing and therefore is allowing to exercise some different performance advantages over a traditional Hadoop cluster storage system approach. It's implemented and supports something called Scala language and provides unique environment for data processing. Spark is really great for more complex kinds of analytics, and it's great at supporting machine learning libraries. We're going to see more of that in our machine learning for big data class coming up in a couple of months. It is yet another open source cluster computing framework, and it was originally developed at MP Labs at University of California, Berkeley, and was later donated to the Apache Software Foundation, where it remains today as well. In contrast to Hadoop's two-stage disk-based MapReduce paradigm, Spark is a multi-stage in-memory primitives that provides up to 100 times faster performance on certain applications. By allowing users to load data into clusters memory and querying it repeatedly, Spark is really well suited for these machine learning kinds of applications that oftentimes have iterative sorting in memory kinds of computation. Spark requires a cluster management and a distributed storage system. So for the cluster management, Spark supports standalone native Spark clusters, or you can actually run Spark on top of a Hadoop yarn or the Apache Mesas. For distributed storage, Spark can interface with any of the variety storage systems, including the HDFS, Amazon S3, or some might be custom solution that your organization is willing to invest into. So now that we have a good understanding of the entire stack and all the applications that we have sitting on top of a typical Hadoop stack, let's take a tour of the Caldera's Quick Start VM and understand how each one of these applications relate to kinds of things we have offered within the VM and kinds of jobs we can run inside the Caldera's Quick Start virtual machines. So next up, let's take the tour of the Caldera's Quick Start VM and run some fun exercises within the environment. See you soon.